The easiest way to test an IP connection is to use the ping command. Ping is a command common to most operating systems, which simply sends an echo request from one host to another. If a reply is received, then it shows that the target host is online. First we will find out the IP address of this host using the ipconfig command. Looking at our example, we can see the IP address is 192.168.2.1.4 and the subnet mask is 255.255.255.0, which is a Class C address. We can also see that the gateway address is 192.168.2.1. Let's just create a diagram showing this so we can be clear. Here is our host. It has an IP address of 192.168.2.1.4, subnet mask of 255.255.255.0, which is a Class C IP address. This means the network ID is 192.168.2 and the host ID is 14. The router has an IP address of 192.168.2.1, which is the gateway IP address, and although the subnet mask is not shown for this, it too will be 255.255.255.0 or Class C network ID. So the network ID is 192.168.2 and a host ID of 1. Remember, the gateway helps us to communicate outside our own network ID or subnet. Often this is via a router as shown here. We can test communication with the default gateway using the ping command by typing in ping 192.168.2.1. Notice a response has been received from the host, so we know it is online and we are able to communicate with it. So long as the host is physically available, we can expect to communicate with this due to us sharing the same network ID of 192.168.2, which means we are on the same subnet. Let's assume we have another host on the same network with an IP address of 192.168.2.186. Once again, the subnet mask would be 255.255.255.0, resulting in a network ID of 192.168.2 and a host ID of 186. We could test the communications again using the ping command for that host. We could also use ping to demonstrate the function of the default gateway by trying to ping a known host outside our current subnet. When we say outside our subnet, we mean outside our network ID, or in our example, the internet. We don't always need to use the IP address to find our host. We can also use the name of the destination. In our example, we shall choose candoit.co.uk. So back at the command prompt, we can type in ping candoit.co.uk. Here we can see that we've received a reply from an IP address of 108.178.419. Let's add this to our diagram. Although again, this has not returned a subnet mask, the IP address falls within a Class A address. So the candoit network ID is 108 and a host ID of 178.419. Remember, we said that not only IP addresses are in classes, but they have a lower and a higher address limit. So if we say a host has an IP address between 000 to 127.255.255.255, then it is a Class A subnet, or the subnet mask is 255.000. If the IP address is in the range of 128.000 to 192.255.255.255, then it is a Class B subnet, or has a subnet mask of 255.255.0.0. Finally, if the IP address is in the region of 192.000 to 233.255.255.255, then it will be a Class C subnet, or has a subnet mask of 255.255.255.0. Notice that we have not included above Class C at this stage, as Class D is used for multicasting and E for research and experiments. And to complicate things even further, some of these IP addresses cannot be used as an IP address. Having said that, once you know the reason why, it then becomes obvious. As a quick example, you cannot have a network ID of 0 or host ID of 0. We shall return to this later. We shall now see a few examples of IP addresses. The first is 192.168.2.186. We can see that this falls into a class C, so the subnet mask is 255.255.255.0. When we describe a network or host ID, we should refer to them as 4 octets, so we shall add a 0 to the end of this. This means the host ID is the last octet of the IP address, which is 186, and once again we shall complete this as a 4 octets, which will result in 000.186. The other host on our network has an IP address of 192.168.2.1.1 and once again falls into the class C range of IP addresses. So the subnet mask is 255.255.255.0. Our network ID is 192.168.2 and we shall add an extra 0 to complete the 4 octets. The host ID is again the last octet of the IP address, resulting in 000.11. The question is, will these two hosts be able to communicate? Yes, because they are on the same network ID or subnet. Let's take a second example. This host has an IP address of 90.245.23. This falls into the class A IP addresses, so the subnet mask is 255.000. This means only the first octet of the IP address is the network ID and the last 3 the host ID. The other host has an IP address of 80.245.23. Once again proves to be a class A address. A subnet mask of 255.000. That means the first octet is used for the network ID and the last 3 for the host ID, 00.245.23. Once again, will they be able to communicate? The answer is no, because although they are both class A networks, the IDs are different. One is 9000 and the other is 8000. We did say earlier that no two hosts should have the same name or address. Look at the host IDs. They are both 00.245.23. It is true that they could not be on the same network ID, but because they are on separate ones, they can be the same. Our final example shows what effect the subnet mask can have on network IDs and host IDs if not set correctly. Here we have two hosts on a class B network, 169.23.0.0. So in this configuration, communication will take place between them. But let's change the subnet mask to the host on the left and see the effect. We've now changed it to a class C. Look at what happened to the network ID. It is now using the first 3 octets and the host ID is the last octet. So now these two hosts are on different network IDs, so will fail to communicate. The lesson is that it's not just about the IP classes, but how the subnet mask can change the network ID and host ID if not set correctly. Let's ping CanDoIT IP address 108.178.419. Notice again a response has been received. This is because the presence of the default gateway, which is able to pass on information outside of our subnet. So far we have seen only successful communication, so let's see what happens if we attempt to ping a host which is not available to us. To do this, we will power down the router, or in our example remove the physical connection between the host and the router, which is our default gateway. Now if we try and ping 192.168.2.1 or the router, a response is no longer received and instead a message request timed out is displayed. As the default gateway is no longer active, we will also be unable to communicate outside our current subnet or ping CanDoIT. We can confirm this by typing ping 108.178.419. Notice the message here is slightly different. First, the reply is from 192.168.2.1.4. Remember, this is our host address. And also notice the message destination host unreachable. Both messages confirm ping is not possible at this time, but they have different meanings. Request timed out means that the path to the host is available, but the host itself is not responding to the ping. This could be for a number of reasons, such as the host being physically switched off, as being here, to being blocked by a firewall, cable breaks, and many other problems. Destined host unreachable does not necessarily mean that the target host is unavailable. Instead, it means it cannot find a path to it. In our case, the default gateway has been switched off, and so our path out to the network no longer exists. When a default gateway is switched back on, we can use ping to verify that communication outside our network is still possible. Another command which is used to test network connectivity is known as traceroute. The command when used with Windows is traceroute. Other operating systems such as Linux use a variation which is simply traceroute. The command is similar to ping in that it requests a response packet from the target host. However, it is more useful when identifying problems which lie between two networks. It provides details of the various network and routes a packet will take on its way to the target host. In our example, we know the default gateway. It is the host which exists within a subnet. Essentially, we have a direct connection to the host, and if we use the command traceroute 192.168.2.1, you will see eventually as a result as a single hop. Let's return to our diagram, and when we type in traceroute 192.168.2.1, a packet of data was dispatched from the host to the destination 192.168.2.1. When the router received the packet, it sent back an acknowledgement, and we can see that the command was successful. This means that the packet visited only one host, which was the target itself. As before, we shall use the command with a name, traceroute.google.co.uk. The first thing we should notice is the IP address 83100221240, which is totally out of our network ID. But why has these hops appeared? Let's reset the diagram on the connections. Here we have our host that sent a packet to the router in the office. It was then sent to the telephone line. Next it was sent to the ISP. It then jumped from the ISP more or less to the final destination, google.co.uk. The major problem with our example is that there is no fault tolerance. For example, it was sent directly from the source to the destination as shown. Either the router became faulty or the line between them became disconnected, then our packet would never arrive. Another problem that can occur is that many thousands of users may want to use the same single line, making them busy and tying up the routers. The internet was first created for military purposes, so communication would not be dependent upon one single point. Communication could be made through routes, even if many failed or a web of routes failed. Let's take the following example. Here we can see a number of routers, and each will be connected to each other in many different ways. We have simplified it here. Each router looks at the neighbouring router and records different things about it. For instance, is it up and running? And if so, is it busier than its neighbouring router? All this information is instantly updated. As soon as a packet is placed on the web, a route from the source to the destination is instantly created. Obviously the shortest route will be preferable, but maybe some of these routes may be down or busy, so alternative routes are computed. In our example, the route that we have taken to google.co.uk was 5 hops. However, if one or more of these routes were down, then another route will be used.